Okay, hi everyone. I must admit it's a pleasure to be here and wonderful to see so many colleagues again after so many years and so many new colleagues as well. So let me also begin by thanking the organization committees for giving me this opportunity to talk to you. So as the title says, I'm going to be talking about modeling the polarized synchrotron emission from AR Sco and RXJ1912. And the reason why I want to do this is because I'm going to demonstrate to you by modeling the polarized emission is going to give us critically constrain the geometry and the parameters for the theoretical models that describe these systems. So let me start by reminding you what AR Sco is. So AR Sco is a white dwarf, M dwarf binary system. It has a 3.5 hour orbital period. And there are two other modulations in the photometry, one at 117 seconds and one at 118 seconds. The 117 seconds is thought to be the spin period of the white dwarf, and the 118 seconds is just the beat period between the spin and the orbital period. But then that's where the similarity to cataclysmic variables stops, because there is no sign of accretion in this system at all. Even though you can clearly see orbital and spin modulations in the photometry, actually through UV all the way through to radio, there's no sign of accretion. There's normal characteristics of accretion you see in spectroscopy, like broad and variable emission lines in the spectroscopy. So instead, this is proposed by Marsh et al. In Nature in 2016 to be the first so-called white dwarf radio pulsar. And so the emission from the UV all the way to the radio is thought to be of synchrotron origin. And here you can see some plots. So since the discovery of the Marsh publication, there have been further follow-up observations in the radio and X-rays as well from most X-ray satellites have followed up. So there's also showing X-ray modulations as well, and also further VLA radio observations. So because there's no accretion in this system, it's thought that the emission is powered by the spin down of the white dwarf, leading to the emission of synchrotron radiation. So for this talk, I'm going to focus on the optical polarimetry, because after this publication, David and I discovered that this system also emits optical polarization. And here's an example of a data set. So this data was obtained with the Hippo polarimeter on the 1.9 meter telescope in Sutherland. And you can see in the upper plot the kind of long 3.5 hour orbital period. And then in the lower plot is the linear polarization. You can also see there's an orbital modulation there as well. And in the next plot, I'm going to zoom in on this highlighted area. So now you can see that all that variability you could see in the previous image is in fact made of all these pulses. So you can see here the top one is the total intensity, and then the lower plot is the linear polarization. And in a matter of 30 seconds, the linear polarization goes from 0 to over 40%. And corresponding to each of these linearly polarized plots, the position angle of polarization rotates through 180 degrees. And there are effectively, so I've highlighted now the area, this corresponds to one spin period of the white dwarf, and you can see it's double pulsed, and each pulse has a full rotation of 180 degrees in polarization. So not only that, the pulses also vary as a function of orbital phase. So in this I'm going to introduce you now to these. These are called, what are they called? Dynamic pulse profiles. Sorry. So this is a color-coded diagram showing how, on the top left one, how the spin pulse varies with orbital phase. So you can see this dashed line here corresponds to the highlighted area in the plot below. So now you can see, for example, for the spin phase, how the spin pulse evolves over the orbital period. It's not there for all of the orbital period. It's strongest at these particular orbital phases, centered on about phase 0.4. But also it has this kind of diagonal structure. And similarly, in the data, in the Fourier analysis, we detect strong beat and spin periods. So we also produce a similar plot showing how the beat pulses vary with orbital phase as well. And you can see they have a location strongest during a certain orbital phase period, but also they have this diagonal shift as a function of orbital phase. We can produce a similar plot for the linear polarization, and you can see here again the linear pulses evolve with orbital phase, strongest at around the earlier orbital phases, but also the pulses split into two in these diagrams. And they also have this diagonal structure between the two. We also detected circular polarization, and it's at a much lower level, but once you've bin the data up, you can see that there's a definite, here the negative polarization is in blue and the positive is in red, but there are regions where circular polarization is preferentially seen. And then we can also do the same for the position angle of polarization. And this is quite a crucial plot because this shows, you can see the angle is color-coded in this plot. You can see how the spin phase pulse varies with orbital phase. The lines are vertical, whereas on the beat phase, the lines look diagonal. Now this is demonstrating that the origin of the synchrotron emission is locked in the spin reference frame. That's why you get vertical lines there. You've got the right period, it's not drifting, and it's not locked in the beat of the system. So this is a critical parameter to get right. Okay, so the next part is now try to model this data, because by modeling the data, we will be able to tell where in this AR Sco system the synchrotron emission comes from. So we tried lots of models, but I'm going to cut to the chase and show you the one that works because we only have a few minutes. So Takatakal theorized that in this system, as the white dwarf rotates and the magnetic field sweeps past the M dwarf star, it will sweep up and accelerate electrons to relativistic speeds. These electrons will then fall towards the white dwarf magnetic poles, and as they reach the magnetic mirror point of the white dwarf, they will emit synchrotron emission. So to model this, we formulated, oops, sorry, I didn't mean to do that. We formulated a beamed dipole radiation to simulate synchrotron emission. So you can see here the green, black, and orange lobes represents the total intensity, linear polarization, and circular polarization. So you can imagine as you rotate this system, you will get light curves that look like the plot on the bottom. But now if we convert this model into the dynamic pulse profiles, like we did with the data, this is what we have. And if we compare this to the observations are on the right, which I showed you earlier. You can see that we're nowhere near yet reproducing the data. So there's a lot of information on the screen here, but the trick here is to do a spot the difference, if you like. And at the moment, there's a lot of differences. So what we did next was, obviously the white dwarf is not isolated, it's in a binary system. So we took this synchrotron model and we placed it in a binary system. And we added an additional variable to our model, in that as the white dwarf has magnetic field has swept past the secondary star, in this region, given by the red arrow, it receives a new injection of electrons from the M dwarf. So only during this region, highlighted by the red arrow, is the synchrotron emission enhanced. Okay, for the rest of the spin period, there isn't any synchrotron emission. So just to summarize, this model now consists of dipole beamed synchrotron emission. The emission is coming from the magnetic mirror points on the close to the magnetic poles of the white dwarf. The magnetic field lines of the white dwarf receive a new injection of electrons every time it passes the M dwarf, and also now we'll get variability because we'll have a different viewing angle as the orbit rotates. So here we go again. We'll do a new comparison. The model on the left, the observations on the right. Now we add this new constraint, and you'll see just by adding this new constraint, we're now reproducing some of these important features, particularly where the pulses are located in the orbital, in the dynamic phase diagrams, but also this kind of diagonal structure between the two. There's a few other differences, but the main difference that still remains is in the observations you can see there's an additional pulse, and we reason that this is just simply emission from the other magnetic pole, the second magnetic mirror point. So we added a second one to our model, and I'll overlay that now, and you can see that we've now pretty much reproduced all of the features in the observations. Okay, so that's that. So that was the story up to about 2018, and AR Sco was the only system of this type. But since then, 4 or 5 years later, we believe we finally found a second AR Sco system, so it's no longer unique. And so it's AR Sco on the left again. The new data is on the right, and you can see the two objects are remarkably similar. They have similar orbital periods. The new system has a spin period of 318 seconds as opposed to 117 seconds. But you can see that the new system, the difference between the left one and the right one is the new one just seems to have one synchrotron emission compared to AR Sco, which has 2. So we took our AR Sco model, and all we did was decrease the inclination of our AR Sco model so that the second synchrotron emission region was no longer pointing in our direction. And you can see that the model creates the data very well. So that brings me to the end, but I have like 5 more seconds left. So during the COVID pandemic, I spent my time learning how to derive animations of these systems. So this is an artistic animation of what I think AR Sco looks like. Maybe I click, oh, okay, I don't click on the play button. Okay, so you can see the magnetic field line sweeping past the M dwarf, and you remember from the dynamic pulse profiles at about phase 0.3, 0.4, so I'll scrub fast forwards to there. Oh, this is annoying how I can't. Can I fast forward to there? Guys, can you help me here? How do I fast forward this animation to?
Sorry, I
Okay, we'll have to show that later. It looks like okay. All right, I'll stop there. Thanks.